Hi, and welcome to IV Tutor. We want to look at search algorithms today, and we have two types of algorithms that we're going to look at. The first one is sequential search, and the other one is binary search. And the sequential search algorithm is very simple because, you are just searching, from start to end. So you actually just go item by item from the first item to the last item, and there's nothing complicated about that. So that's why it's called the sequential search algorithm, because you search your item or your list in sequence, starting from the first element down to the last element. So if you have, let's say, a list with 100 elements, in the worst case scenario where the item is not in the list, it means you are going to have to make 100 comparisons. So on average, if you've got n elements in a collection, on average, we are saying that the sequential search algorithm searches an item an average of n plus 1 over 2 elements, which means if you've got 1,000,000 items, on average, we are saying it searches about 500, it makes about 500,000 comparisons, because remember, it has to go index by index saying, is this the item I'm looking for? If not, it goes to the next index. Is this the item I'm looking for, until it has exhausted the whole list. So you can see that it's very inefficient for very large collections because it has to compare every single item. Another search algorithm that we are going to look at is the binary search algorithm, which uses the divide and conquer method. But if you're going to use the binary search algorithm, your list must be sorted. So we will never apply the binary search algorithm on an unsorted list, right? Which means you never get a question that says, use binary search algorithm on this array and the items are not sorted. It doesn't make sense. So, we'll discuss this in more detail very soon. But if you compare the binary search and sequential search algorithm, you can see that the binary search is a big O of log n, whilst the sequential search is a big O of n, which means that it's less efficient because you want your running time to be less. But in this case, so the higher the big O, the higher the running time, which means it takes longer to execute. And the lower the big O, which means the lower the running time, which means it executes faster. So, just to remember, sequential search is a big O of n, and binary search is a big O of log n. I won't delve into the actual details of how we get to log n, but if you're interested, you can obviously go into the recommended textbook. There's a whole detail on all the calculations leading into this conclusion, but we are not doing that. We are just going to focus on the material that matters for the exam, right? So, in the binary search algorithm, if you are looking for an item, because your array is sorted, and let's say you're looking for 89, right? The binary search algorithm simply says, check the item in the middle. So if we are looking for 89 in this case, and there's 39 in the middle, we know that because this middle item is less than the search item, we don't have to bother ourselves with this bottom half of the collection, because 89 is above 39. 89 is greater than 39, which means because it's sorted, we definitely know that it's not here, which means our focus then needs to be on the top half of the array, which means this here becomes our search list. So whenever we are using binary search algorithm, that is the most important thing that you need to be mindful of. So this here, when you start your search, this here is your first index, and this here is your last index. So first and last are used to demarcate your search array, and this here is your mid index, which is the middle point of your array. So after comparing with your middle element, you can then, like in this case, we said we are looking for 89, which means we know it's not in the bottom half of the array. So our first then becomes this guy, because this becomes our new search array. This remains our last index. And obviously we have to calculate a new mid index, which we simply calculate by saying first plus last over 2, in which case we get 8, which means this becomes our new mid index. Okay, so that is what we want to talk about and see how you apply the binary search algorithm. Here I'm just showing you the basic concepts around the binary search algorithm, which means as you keep on searching, you keep on shrinking or dividing your array and focusing in the range where your search item is most likely going to be, because your items are sorted, right? So in terms of the binary search algorithm, I think it's also just a bit important to understand how the code looks like, but you rarely get questions on code, but it's also quite important to understand what's really happening, because we said that when you start, your first index is the first item, your last index is the last index. So you can see that we start off by initializing first to 0 and last to our last index, length minus 1. You know that arrays are 0 indexed, which means if you have 10 items, then index number 9 is your last index. And then we've got mid. So you want to keep on repeating this process that we explained here until eventually your first index is greater than your last index, or until your last is less than your first index. So you keep on moving first or last. So first moves upwards or last moves downwards until first becomes less than last. If that happens, it means that you did not find the item. So you keep on repeating this process until you find the item at the middle of at the mid index, or you keep moving until first becomes less than last, because that will show that you did not find the item in your collection. So you can see we start off by setting first to 0, last to length minus 1, which means last points at your last index, and then you've got mid, which is going to be pointing at your middle index. And then we've got a Boolean variable found, which is initialized to false because we haven't found it. If we find it, we then say true, and then we return. So the middle index is calculated by taking the first index plus the last index over 2. This is very important because you're going to be doing this every single time you want to recalculate which one is your mid index, like you saw me doing here. So we said, like, if we move first to this index number 6 and last is still index number 11, we can then calculate our mid by saying equals first, which is 6, plus last, which is 11, over 2. You get 17. And 17 over 2, these are integers, which means you get 8, not 8.5, just 8. And then this becomes your mid index. So it's quite important for you to understand how this code works, just so that you understand the algorithm better. So that's how you calculate your mid index. And then you are going to then check if the mid item is your item, because if it is, then you found it. Otherwise, you're then going to consider whether the item you're looking for is greater than the middle item or less than the middle item. If the item you're looking for is greater or is less than the mid item, it means you want to discard the top half of the array, which means your last must then shift and be the index just before mid. So what we are saying here is that if, for instance, in this case, we were looking for 1 or 2, and this was our mid, and we find out that, well, the item we are looking for is less than mid, we then need to, our first obviously remains pointing here, because we want to focus on the bottom half of the array, which is this here, which means our last index, which was here, is now having to shift and be this guy, because we only want to focus on that, this middle, because the item we are looking for is less than the mid, which means your last becomes this guy. So in other words, you are saying that if your search item is less than mid, your last index becomes your mid index minus 1. And if the item you're looking for is greater than the mid item, then your first index becomes mid plus 1, because you want to move first to here, if that is the case. So it's either you're going to shift your last from here to here, or you will shift your first from here to here, so that this becomes your search array. So that is what we are seeing in this if statement. It's a very basic, statement, condition rather, which is simply saying if the search item I'm looking for is less than the mid, then let's shift last to mid minus 1. Otherwise, if it's greater, let's shift first to mid plus 1. And then we repeat as long as we haven't found it, and as long as our first is still less or equal to last, which means you're going to keep doing this until first becomes less than last. Until last becomes less than first, because that means you did not find the item, and this will then return. So this is now saying if found, which means if this was true, if this is found, because if you find it, you essentially want to then exit the loop, and then you can say if found, return the middle index and say this is the index where we found it. Otherwise, if we exit the loop and we didn't find it, then we simply return -1, which means we did not find it. That is the idea behind the binary search algorithm. Now let's look at an example and apply the binary search algorithm. So mostly when you are applying this algorithm, I recommend that you write the index of each element at the top of your array so that you can keep track of the index instead of trying to recalculate or counting the index every time you go into the next iteration. In this example, though, well, you don't have to do it because the items are also the indices. So it's unlike the first case or the example that we were looking at, where we have to put the index at the top, but it's really recommended to put the index at the top so that you can keep track of your index whenever you apply the binary search algorithm. Now, if we look at this question, it simply says, here's an array, apply the binary search algorithm, you are looking for 11, right? It's not there, so you don't just go, oh, not found. They want to see how the binary search algorithm is going to apply, to be applied in this case, looking for 11 in this array. And you're going to show the results by giving the values of S list first, S list mid, and S list last, which means show us the values at these indices or indexes. So to do that, you just create a table, you say, here's my first, mid, and last, which means you have to keep track of the index. In this case, I'm not going to write 0, 1, 2, 3, 4, 5 at the top again. I'm just going to, just use these numbers because they are also the indices. So in this case, you are going to start off with your first sitting here and your last sitting there, which means your mid is going to be first plus last over 2, which is 0, plus 10 over 2, which means your mid index is 5, which means this becomes your mid index, right? So normally you want to keep track of what first is and what last is. So I also recommend that if you can, just write what your index for first is, what your index for mid is, and what your index for last is, so that you can, make your adjustments without a lot of confusion. So normally you just put this in the corner there, but what we actually want is the value at that index. In this case, or it's the same thing, right? 0, 5, 10. So I may not have to do double work. I can just ignore this part. But I'm saying this in case you're dealing with an array that is different numbers, like the first example we looked at. But in this case, the index is the value. So I'll just write it like this. And then we compare if the mid item is our search item, which is 11, and it's not. And then we say, okay, so is this less or greater than our search item, or our search item is greater than 5, which means we want to discard the bottom half of the array and focus on the top half of the array, which means your first becomes mid plus 1, which means your first index becomes 6, your last is still 10. And then you recalculate your mid, which is 10 plus 6 over 2, you get 8. Therefore, 8 becomes your mid index. And then you compare, is 8 less or greater than 11? Since it's less, it means you want to focus on the top half of the array. That means your first becomes mid plus 1. So your first, because your first was here, your last is here. And since this was your mid item, now your first should be here because you want to focus on this array. So your first becomes mid plus 1, which means it becomes 9. Your last is still 10. 10 plus 9, you get 19. And then, so you're going 9 plus 10 over 2, you get 19. And 19 over 2, you get 9, right? So 9 becomes your mid index. Remember, you're dividing integers, so there's no 9.5. Okay, so you get 19, but by 2, you get 9. 9 becomes your mid index. You compare your mid index with the search item. Again, 9 is still less than 11. What do? You increment your first. So first becomes 10. Your last is still 10. Your mid is now 10. 10 plus 10 over 2, 10. And then you compare the middle element with the search element. Your search element is greater than 10, which means first becomes 11. Last is still 10. And because of this condition here, it means that your loop terminates Therefore, it doesn't execute anymore when it sees that your first is now greater than your last. And that way, your answer is simply this table that we have. So that is how your values of first, mid, and last will go as far as the binary search algorithm is concerned. And in this case, we did not find the item that we were looking for. Okay. Another example, so you can just pretty much keep on applying this over and over again on different questions. Here's another one, but this time we are dealing with different values, and they said this one is called S array. I think I was too lazy, I just maintained S list here. So don't worry about that. You just have to put this as S array, and the same goes here, and the same goes here. But it's basically the same table. And in this case, this is where I like to put the index at the top of the numbers, because it will help you, just look at your values, know exactly what you're looking for, and put your values inside the array. So as you start, your mid equals first plus last over 2, which is equivalent to 0 plus 11 over 2, which gives you 5, right? So that means your first index is 0. Your last index is 11, your mid index is 5. Now you see what I'm talking about. This will just help me look at this array and know exactly what values to pick. So I've got 10 at index number 0, I've got 41 at index number 5, and I've got 100 at index number 11. Then what am I looking for in this case? We are looking for 100. So then we compare 100 with 41. It's greater, which means our first needs to shift up. Therefore, our first becomes mid plus 1, which is index number 6. Our last is still index number 11. Our mid is now 11 plus 6, which is 17 over 2. And we get 8. Therefore, 8 becomes our mid index. And then if I look at index number 6, we have 45. At index 8, I have 68. At index 11, I still have 100. Again, 100 is greater than 68, which means our first shifts up, which means our first becomes 9, mid plus 1. Last is 2, 11. 11 plus 9, that gives us 20. Over 2, we get 10. So 10 becomes our mid index. And if I fill in the values, we have 70 here. We have 90 here. We have 100 here. Again, our mid item is still less than our search item. Therefore, we shift first upwards. Therefore, first becomes mid plus 1. That becomes 11. Our last is 11. Our mid therefore becomes 11. And at this point in time, we have 100 here, 100 here, 100 here. We compare 100 with our search item and we find it. And this here and here we stop. And you don't have to put these values. So sometimes if it's a written exam, you can just use a pencil and just erase this afterwards, because this is not important for the question. What really matters are just these values. So you can see it's very easy to apply the binary search algorithm. But there is one question that was very interesting as far as the binary search algorithm is concerned, because here they said, well, let's see your approach. Can you apply the same mindset if we are to use 2 midpoints, and instead of splitting the array into 2 sub-lists every time, or you're partitioning it into half, what if we partition 3 times, and then which becomes a ternary search, because bytes 2 try 3. So here they say complete the partial implementation of the C++ function below that performs a ternary search. A ternary search is an extension of the binary search. Unlike binary search, it partitions the elements to be sorted into roughly 3 equal parts. Then it checks in which one of these parts the given integer will be. This process then continues until the given element is found, or until it is clear that the element is not in the list. And then there we go. So you had to apply your mind in this case and say, okay, if I have a collection of items, and instead of using 1 midpoint, I now have 2 of them. So you're going to split this into 3 portions, and you have, midpoint 1 and midpoint 2, right? And remember, it's a sorted array, which means if the item that you're looking for is less than midpoint number 1, pretty much your last should come here and your first remains here. If the item you're looking for is greater than midpoint 2, then your first should just become here and discard all of this because it's sorted. So your first becomes here and your last. So this becomes your search list. If the item you're looking for is greater than midpoint 1, but less than midpoint 2, then you want to focus on this part, which means your first becomes midpoint plus 1, somewhere here, and your last becomes midpoint 2 minus 1, which means it comes here. So this becomes your first, this becomes your last, and you focus on this part. So all you are doing in this case is choosing which portion or partition of this array you're going to focus on, and then shift your first or your last according to that. So if we are focusing on this part, then your last becomes midpoint 1 minus 1. If you're focusing on this part, then your first becomes midpoint 2 plus 1. If you're focusing on this part, then your first becomes midpoint 1 plus 1, and your last becomes midpoint 2 minus 1, which means it will be there. And that was all that was required. So you can see in this case that they said first equals 0, last equals last index. So first is here, last is there as usual. Then they declare the 2 midpoints, and they say as long as first is less or equal to last, which is the same condition, we want to. So here you can see they calculate the midpoint for you already. They say midpoint first plus last, da da da, midpoint 2, da da da. So this was already done for you. Now your code is to just determine where to put first and last. That's your if statement. In other words, you're saying, or if the item you're looking for, the element X, is less than the item at index midpoint 1, then we focus here. If it's greater, then we focus here. Else, we focus here. Because if it's not less than M1 and it's not greater than M2, then it's in between, right? So you can just go if, else. So that means your if statement would then be something like this. So I'll go here and be if, let's see if we can change this so that it's clear when I type it. Okay. Yeah, so you go if, so I'm looking at the element X and going if X, right? And here you're using a vector, so obviously you're going to, it behaves like an array. So I can say if the element X is less than midpoint 1, which is mid 1 in this case. So my vector is A at mid 1. So if the item I'm looking for is less than midpoint 1, then that means my last becomes midpoint 1 minus 1. So I can say last equals mid 1 minus 1, because I want to focus on the bottom half of the array. And I can go else if my X is greater than the value at mid 2, which is the second middle point, which means I want to focus on the last portion of the array, then my first becomes mid 2 plus 1. Otherwise, well, my first becomes mid 1 plus 1, and my last becomes mid 2 minus 1. That's my if-else statement, and then I loop again. So that is what I'm going to do here, if that's clear. So if we walk through this again, all I'm saying is that if the item we are looking for is less than the item at mid 1, which means we are somewhere here. Therefore, let's shift our last to here, right? Mid 1 minus 1. So our index becomes there. If the item we are looking for is greater than the item at midpoint 2, then let's shift our first to come here so that we can focus on this portion of the array. So therefore, our first becomes mid 2 plus 1. Otherwise, well, this is the only option left. That means our first becomes mid 1 plus 1, which means our first starts here, and our last ends here, which is mid 2 minus 1, right? So this is how you would then adjust your first and your last. But there's one thing that's crucial, which is still left. What if we find it? So your item is either going to be mid 1 or mid 2, which means you can then have another condition that checks for whether or not we found it. So we can say here, if X is equal, if our X here, let's see if I can just make this the same size. Yeah. If our X is equal to the item at vector mid 1, But here you have to check 2, right? Or maybe if it's not at the first mid, it could be at the second mid. So you can say, or x is equal to a mid 2. This means that we found it, right? So we can just say, well, we found it, which means in this case, we can return, well, let's see. Yeah, we need to return the actual index. So in this case, we don't know. So I can say, I have to do this in separate if statements. So I can say if it's at index at the first mid, then return mid 1, right? Else if it's at the second mid, then return mid 2, like that. So if we find it at the first index, at the first midpoint, then return the midpoint. If we find it at the second midpoint, then return the second midpoint. So what I'm doing here is just more or less the same thing that we have done here, where you are simply saying, well, or in this case, we return right at the end and we use a found Boolean. But in the current question that we are doing, we're simply saying, if we find it, just return the index and not have to keep on looping. So that is another way you could have written the same algorithm. So instead of using the found Boolean, you can just say return if you find it immediately, which is more or less the way we are doing it in this current question. So that's our, so you need an if statement to check whether you found it or not, and then you need an if statement to check to adjust your first and your last. So pretty much this is how you would then conclude your whole logic for this question. So it really required you to apply your mind and think about, okay, so I'm now using 2. So it's either what I'm looking for is either going to be here or going to be here. If it's not this and not that, then the next thing is to adjust first and last and decide whether to focus on this section or this section or this section. So you would then adjust your first and your last accordingly. And that's binary research for you. I'm not going to do a lot of examples because it's literally the same thing that you have to keep on doing every single time. I just threw this question in because I found it very interesting and a good thing to discuss. Otherwise, you just have to keep on practicing more binary search questions. They are very simple. It's very straightforward. There is not much code involved in most cases, except this question that I've seen. Otherwise, with enough practice, it should all make sense. Otherwise, yeah, that's it for this one. I'll see you in the next one. Cheers.